Okay, so we started with chapter 9, 9.1, the nature of waves. Remember, waves transfer energy, okay? And we talked about these ripples and how a rock hits the water and transfers energy to the water. Remember, again, right here, all waves, whether they are water waves, sound waves, light waves, or earthquake waves, have this property. They carry energy without transporting matter. There are, and we talked about mechanical waves. Mechanical waves need a medium, and there are transverse waves. Remember, a medium is the matter through which the energy or the wave travels. Transverse waves, these type of waves up and down, energy moves at right angles. And then there are longitudinal waves where the movement of energy is in the same direction that the wave travels, okay? So right angles and in the same direction as the wave travels. And seismic waves are both transverse and longitudinal. And that brings us to section 2, wave properties. All right, so I talked before about drawing this right here, and I told you this would make more sense. Okay, so right now, let me change colors because it'll help us a little bit here. Pink, why not pink? Okay, so right now, if there is no disturbance or there's no energy, the wave lies flat. Okay, the wave lies flat, and this right here, this bar right here, this is called the rest. Okay, this is the rest. There's no energy right now, so I'm going to have just a flat bar. It's at rest. But as soon as energy starts, we'll move down here a little bit again. As soon as we get a little bit of energy, depending on whether it's a transverse wave or a longitudinal or a compressional wave, we now have this going on. Okay. As soon as there's a little bit of energy and there's a disturbance, I start to get, and this is a little difficult to do, believe it or not, on this drawing pad, I start to get a wave. Okay. I get a disturbance. Now, the reason a transverse, and I drew a transverse wave here, when I add energy, what happens is the wave moves up and the energy goes this way. Okay, so the more energy there is, the higher this wave's going to be and the faster it'll move this way. Okay, so, well, not necessarily the faster it's going to move, but the higher it's going to move. And we're going to talk about this right now. Okay, so transverse waves move at right angles. The energy moves at right angles. Okay, at a right angle. All right, and in a compressional wave, we'll just draw one of those real quick too. Why not? It's not going to hurt anything. In a compressional wave, then, we're going to get, I'm going to draw it real close here to this. There's our rest. And let's make our compressional waves blue today. I don't know. Okay, so here's my compressional wave. Remember, it's laying flat on that rest until energy gets involved. And then my energy is going to cause the wave to do one of these things. Okay, there we go. And the energy here moves in the same direction as the wave. Okay, so at right angles and then in the same direction. Now, these waves have properties. Properties. I said that kind of odd. Okay, and I'm going to draw it all out, if I can here, on one wave. And I'm going to make this a transverse wave just simply because in tests, you very rarely have to identify, in a standardized test, you have to identify the properties of a longitudinal or compressional wave. But we will go over those. Don't worry. We'll do that too here in a minute. All right, let's change our color. Whoops. Boom. just pretty pink, I don't know. Okay, so here is our transverse wave. I'm going to draw one in here. And again, I'm going to do the best I can. It's not the easiest thing in the world to draw. Okay, so here it is. Now let's label this baby. I'm going to pick a new color to label. I don't know. Let's do a light blue to label this wave. Okay, so now we have properties. Now, I'm sure you learned some of this in middle school. Okay, this is the crest of the wave. Here's the crest. The lowest point is called the trough. So I have crests and troughs. This area right here, inside here, is called the amplitude, or amps. You can measure it crest to rest or trough to rest. Either way, it doesn't matter. This is the amplitude. Okay? Now, we also have what's called the wavelength. And the wavelength is going to be one crest and one trough. Okay? And this right here, this area, I'm going to go like this so I'm not making a big mess out of things. From rest to rest and trough to trough. Or one crest and one trough is known as the wavelength. And we use the Greek letter for the wavelength. We use the Greek letter lambda. All right? Looks like that, lambda. Now, this is one wavelength from one complete crest and one complete trough. Now, I know what it shows over here. It shows from crest to crest or trough to trough. But let me show you something real quick, and this will help, I think, why I measure one complete crest and one complete trough. All right, so if you look at this picture here, this is an actual earthquake wave. Okay, it's a P wave, and our problem here is it's hard to tell. It's much easier to look at this and find a crest and a trough than it is to try to go from crest to crest. Okay, especially in here, you can see crest. Is this a crest? Where's the crest at? Is this little spot of crest? So you take a top point and then the next bottom point, and that's your wavelength. Over here is really nice to see. Okay, and I just think it's easier for me. It's easier to go from crest to trough and measure it in that way. Different people measure it different ways. That's the way I like to do it. So either way is correct. So it's up to you which way you want to measure it, all right? As far as a longitudinal wave goes, let's draw a longitudinal wave real quick. Let's get some blue on here. And here's a compressional or longitudinal wave. Okay, so these areas where it is spread out, the areas here where the wave is spread out, it's called a rarefaction. Rarefaction. Where it's jammed together, we'll go from right here to right here, where it's jammed together, that is a compression. So where it's jammed together is compression, where it's apart is a rarefaction. Now, just like in the transverse wave, I can measure amp inside or outside, or in the trough, or in the crest here. I can do the same down here. I can go where the rarefaction is. This could be my wavelength, I'm sorry. Holy smokes. Not my wavelength. My amplitude. This could be my amplitude. And this area right here where it's compressed, I can also measure my amplitude there. Now, just like here, up here, say this is a sound wave, okay? And you can hear my voice right now. If I add amplitude to get this to go up, my voice is going to get a lot louder. The louder my voice is, the higher the amplitude. The softer my voice is, the smaller the amplitude, okay? So the higher my voice, the louder my voice, I should say, the higher the amplitude, the lower my voice, the smaller the amplitude, okay? And here, wavelength, again, is going to be one, from here to here, one compression, one rarefaction is our wavelength, all right? Now, a couple more things I'll talk about with these waves real quick. There is, it'll be easier if I just come up here and I draw it for you. I'd rather draw than, it's just easier for me. I'm going to go here. I got a lot more room right here. Boom. Boom. Okay. So I'm going to pick some different colors and I'm going to show you how this works, okay? Here's some orange. This will work really good. We're going to use orange for talking very softly and deep. Hello, hello. So when I talk with a deep tone, oh, like this, my waves are going to be spread out, okay? If I talk softly with a high voice like this, hello, that's softly with a high voice, I'm going to get this. The higher the tone or the higher the pitch, the closer together the waves are going to be. The higher the pitch, the closer the waves are going to be, okay? So that's soft. Let's do something loud. Ooh, rainbow. Now I'm going to go low and loud. Oh, oh, ah. Notice higher pitches, it's closer together. Lower pitches, it's spread out more, okay? And the more energy I put into my voice, the higher the wave's going to be. The less energy I put in, the lower the wave. Okay? So that deals with wavelength and frequency. Frequency is how many waves pass per second. Frequency is how many waves pass a given point per second. Okay? So here we go. This would be a low frequency, and this right here would be high frequency. The wavelengths are closer together, higher frequency, okay? Now we can measure the speed of a wave right here. V equals F, or speed. Remember V, speed equals the frequency multiplied by the wavelength, okay? Multiplied by wavelength. Frequency multiplied by the wavelength. Get that a little better there. There we go. Multiplied by wavelength, okay? Again, speed is always in meters a second. Frequency is in hertz, and wavelength is in usually micrometers. We'll talk about that more though. Amplitude, again, amplitude is high, louder or softer. Louder. The louder it is, the higher the amplitude. Okay. High amplitude. Low amplitude. Okay. So again, the more energy in the wave, the more amplitude. Low amplitude means there's not much energy there. Okay. The higher the amplitude, the more energy there is. Okay, that's where I'll stop right now. Hopefully this is going to help you. And I will say good luck.